Hi there students, this is Dr. John, your physics and math professor. Today I'm going to explain how we get the lens formula and the magnification formula for thin lenses and thin mirrors. Over here I've drawn a couple of converging objects here. Here's a converging mirror, here's a converging lens. Remember, it's very simple. The object comes in here, the object in green comes in here with a ray of light that's parallel to the principal axis, hits here, comes through the focal point right there, and we have another ray of light that goes through the center of curvature. It bounces off the mirror, comes back, and where they intersect, we have the image. Similarly, over here, we have the one ray of light that comes here through the focal point. However, the second ray we take through the center of the lens rather than through the center of the curvature like we do with the mirror. And where they intersect, we also have an image. Both of these are real images. They're upside down. I drew them in red here for you. Nice thing about ray diagrams is you can, if you have the approximate location of the object, you can get the approximate location of the image. But if you want the exact location of the image, then you need the exact distance of the object from the lens or from the mirror, and you can actually calculate the exact distance to the image as well using this formula over here. And you can even calculate its magnification. Its magnification in this case is negative because it's flipped upside down, and it's less than 1 because this is whatever height this is less than that height. So this is less than 1. So where do we get these formulas though? In the work that we've done so far, it just seems like they've been pulled out of a hat and given to you. So I'm going to actually develop it for you. I could use this picture, or the two pictures for a diverging mirror or a diverging lens. I could use any one of those four to show you how we get it. But the simplest one to use is this one over here, which is a duplication of this one, a converging lens. Now, just to repeat, we have the object over here. One ray of light comes in here, hits this lens here, comes down, hits the focal point, comes here. The other one comes from the top here as well, comes through the center of the lens, and comes over here where they hit, we have an image. Now, just to remind you, this is an image. This is a sort of an abbreviation for a converging lens, for a convex lens. It looks like this. The arrows on the end go like that, which sort of is shorthand for if you wanted to draw the whole lens like that. You draw the whole lens like that, but if you don't have room on your paper, sometimes people will use this as an abbreviation. If I drew all that lens there, it would mess up a lot of stuff that I'm trying to illustrate for you. So just having those arrows on the end, just think of it as continuing. If you had the other arrows on there, if you had it like this is sort of an illustration of how you would start thick and go thinner like that. So this would be a diverging concave, double concave lens. You normally wouldn't draw the middle in a case like that. So this symbol over here, if you draw that symbol, that would be the other kind of lens, which we're not using today. I just wanted to show you those two symbols. So now let's go to how we develop this. So what I have over here, you may notice this, I drew this in red and in blue. So I drew two triangles here. One triangle goes here to here, and then down to here, and then back up here. Those are the three sides of the triangle. The other triangle is in blue inside here. It's from here to here, and then from here down to here, and then here to here. So I've drawn these two triangles here, sort of overlapping each other. Some of the lines overlap each other. These triangles are actually similar triangles. What does it mean to have a similar triangle? So here I have a picture of similar triangles. I have two triangles. They look sort of similar, just one looks a little bit expanded. This looks a little bigger than this one. Notice the angles. This is angle alpha. That's also angle alpha. Same angle. This is angle gamma. That's the same angle gamma, beta and beta. If two triangles have the same angles in that order, A, B, C, alpha, beta, gamma, just like that, then they are similar, which means that whatever the size of this one is, it's just blown up over here because the angles have to stay the same. And one of the cool things about similar triangles is the ratio of the sides are the same. So for example, if I took the ratio of the side B over B, so big B over little b, this one over this one, that's also the same as big A over little a. The ratio of the sides plus the ratio of any relationships. So let's say I take this triangle over here and I go from here all the way to this drop down line over there. And I do the same thing over here. Well, the relationship of this length over here to this smaller length over there would again be the same as the relationship of this side C to this side C. So that's the cool thing about similar triangles, and we've got two similar triangles here. How do I know that they're similar triangles? Well, just take a look at this with me here. Notice that there's this line over here, which is your principal axis, is parallel to this line over here. And then we have this red line that cuts that, creates an angle there and an angle there. So if you have parallel lines like that, and you cut that, this angle here will be the same as this angle here. It's pretty obvious on the drawing, but this is part of what you learn in geometry. So this angle alpha is the same as that angle alpha over there. And similarly, notice that they share an angle over here. The two triangles both share this angle here. So obviously that angle is the same. And this angle over here is another one of those where this parallel line and the principal axis are cut by this line. So this whole angle here, gamma, is the same as this angle gamma. So these two triangles, the big red one and the little blue one, are similar triangles, which means the ratio of something on the big one to that on the small one will be the same as the ratio of another side of the big one to the small one. So I went through a whole bunch of different iterations of those relationships, big ones to the little ones, to see if one of those can help me to derive the lens formula. And I found this over here. So I'm just going to show you how this works. So first of all, we're going to have the object, the relationship of the ratio of the object to the focal length. So the object would be this one here. It would be all the way from here to here. Notice I'm just using positive lengths in this case. All the lengths are positive. We're just looking at distances. The distance from here to here. And notice on the little triangle here, the blue one, that would be the same as this distance over here. So this big distance on this big triangle would be the same as this one, which is the distance to the focal point, or the focal length here, the focal length. So 0, or the object, over f is something from the big triangle to the little triangle. Can I relate that to something else from the big triangle to the little triangle? Well, let's take a look at this over here. The object plus the image over the image. So the object plus the image would be from here to here, that's the object, and the image would be from here all the way to here. So this is the distance to the image. You notice the image is over here. So this distance is the distance to the image. This is the distance to the object. So it's this entire, take this big red triangle and go all the way here until you come to the edge. This distance over here is what I have on the top. That's a big distance from the big triangle. That same distance from the little triangle would be starting here all the way to here, which is what? It's the distance to the image from here all the way to here. So that's the distance to the image. Big triangle over little triangle equals something else from the big triangle over the little triangle. So let's see if we can simplify this and find the lens formula in some way. I'm going to start off by taking this I and multiplying it over here. So now I have IO up there, and this just goes away. So that's just O plus I. I'll spread those out a little bit. Now, I would like to have something so that I will have F in the denominator. Well, I already have F in the denominator here, but I would like to have, so it'd be nice to have the same thing on the top. Here I have an IO or an OI. So what if I take this O and multiply the top and the bottom by I? Now, I'm not changing it. This is still valued O because the two I's will cancel. And I'll do the same thing over here, only I'm going to multiply the top and the bottom by O. So here we have F, I, and O in the denominator, just like here. This order should be a little different, but and then we have an IO on the top, IO on the top, and IO on the top. We can divide everything through by IO, and this is going to become a 1, this will become a 1, this will become a 1, just like this. 1 over F is equal to 1 over the image plus 1 over the object. Of course, we could flip these two around, the order of these, just like I have it here. So we've just developed the lens formula for you there. So the hard part about this is figuring out which relationship of the triangles, the similar triangles, will get you this. It may take you some doing, but once you've sort of figured this out, then hopefully you can do that yourself as well. So now let's look at the magnification, and I'm going to do something very similar. I'm going to also take a relationship from the big and go over something from the little triangle. So since we're dealing with the heights this time, I'm going to be dealing with the heights of the object. So here's the height of the object plus the height of the image over the height of the image. Now what is that? That is this height, that's the height of the object, plus the height of the image, which is this height. Now normally in our sign convention we take this as a negative height. However, because I'm just dealing with geometry, I just want to have distances. So I'm just looking at this distance. So this distance plus this distance is this entire distance here. That distance over the height of the image. What's the height of the image? That's over here. That's the entire distance up and down for the little triangle. This distance from here all the way down to here is the entire height of the entire big triangle. If you can see that, it's from here all the way to here, the entire big triangle. Whereas that second thing here is just from the here down to here of the little triangle, which is just the height of the image. So here again I have a triangle relationship for the big triangle over the little triangle. And that again, I can use the same equality there that I did here, which is related to the distances of the image to the object, which is the big triangle over the little triangle. So that's going to be O plus I over I. Now let's see if we can simplify this in some way. Well, this first term here will be HO over HI. So I can move that over like this, over HI, plus, I'll just take this thing away there, HI over HI. I'm just spreading out the denominator there. And this one over here, I can do the same. I can make this one over I like this, and this one over I like this. Now notice here, this one is equal to 1. I over I is equal to 1, and this one's equal to 1. It's HI over HI. We have a 1 on each side. This is a 1 as well. We have a 1 on each side. We can subtract a 1 from each side, and we're left with this. Now this looks exactly like very similar to our magnification formula. We like to have the height of the image on the top. Both of these are sort of flipped from this, so let's flip both of these. We'll go HI over HO is equal to I over O. So here we have created this magnification formula. Now you may notice, if you're looking carefully, that something's missing. Well, what we did here previously is we took the height of the image being just a positive because we just wanted the distances involved here. But the height of the image, the way we define it, we define the height of the image as negative if it's going down like this. And so what we do then is we'll put a minus sign in there to correct for that. And now we have created this entire lens formula right over here, the magnification portion. This is actually equal to the magnification as well. So the height of the image over the height of the object is the magnification, and this here is a way of using the distances to the image and the distances to the object as a magnification as well. So solving this problem was all pure geometry. You're probably not going to need this for high school physics, but it's nice to be able to know this. If you know this, you know more than many of your other fellow students. I hope this helped. If it did, like and subscribe. And remember, my website and my YouTube channel will help you solve not just your physics and math problems, but all your problems, your relationship problems, your personal problems, your financial problems, any problem you have, I can solve. I hope that helped. If it did, I will see you in the next video. Bye-bye.